Uh, Ooh, question 1A, yeah. We got ethanoic acid, yeah, and ethanoic ion, yeah. Safe. Ethanoic acid reacts with propanol diol to form a polyester, yeah. Go to repeating unit. So the best way to do this here is just draw out the two reactants here. So that's just gonna be the the diol situation, yeah. So that's gonna be OH there, bang bang like that. You get it? That can easily be achieved if you just look at that CO, CO, and whatever. Yeah, don't be scared, yeah, to like draw it out and get like, you know what I'm saying? Get dirty with it, bro. You get me? Like sometimes you go to, and then shit becomes clearer, even if it seems like it's long, yeah. Alright, calm. Same shit here. Draw this shit out. So that's gonna be bang, bang, bang. OH, H, 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 H. Alright, safe. So obviously, when this forms a linkage here, it's gonna be the OH there and the H here gonna form H2O. Calm, safe. So that's gonna produce what then? So yeah, so just to draw a linkage here, just connect that. So connect that, yeah. So the H and the whatever is gonna go, yeah. So you're just gonna be left with the O here on the right. So like that. And then it's gonna wrap round as well from both sides. So the H here is gonna fuck off and it's gonna be a straight line. And H here is gonna fuck off, it's gonna be a straight line, yeah. So that's it, that's the answer. So C C O C C C O and then it keeps going, yeah. That's the repeating unit there. Alright, calm, safe. Explain why polyesters are biodegradable, yeah. So obviously polyesters, yeah. Listen, man, if you want to A star, yeah, you need to start talking like these man talk. You get me, yeah? You need to use exact, like you need to be correct. You get me? So obviously, yeah, so obviously polyesters, yeah, they got CO, C double O, that kind of situation, yeah. So obviously those are polar. You're gonna have delta positive and delta negative on those, yeah, which means it's gonna be susceptible to nucleophilic attack since we have the delta positive on the carbon. So therefore it's gonna be yeah, you get it. So that's the situation there. You go use this kind of wording, yeah. Whereas the bonds in the other shit, what's it called? Polyalkanes, yeah. Alkenes are polar or non-polar, yeah. Alright, that's all you got to say for that 2 marks. That's 2 marks solidified, bro. Yeah, easy 2 marks here. Alright, so, whatever, bro. You know how we roll when we do these questions. We skip it. Alright, you know what? You know what? Yeah, let me just roll through. Let me not just skip to the working here. Let me actually read it with you, man. Yeah. So understand this. Understand this. Yeah. Eliminate the waffle here, and take a standard solution is made by dissolving that much grams into water and making up to 250, yeah? So in the 250 centimeter cubed volumetric flask here, how many moles of Na2C2O4 do we have here? In that 250 centimeter cube, we've got 0.162, that's 162 milligrams in grams, yeah? Divided by MR, yeah, which is 134, it tells you that. That's going to be 0.00121 mole, yeah? Alright, calm. So that's in that amount, yeah? Are we talking about that amount? No. He's taking 25 centimeter cube of that and then he's gonna react it with some with some acid or some shit to try to titrate it, yeah? Not acid, but you get the point, you get what I'm trying to say, yeah? To titrate it, yeah? Alright, with the manganate situation, yeah? So therefore, take this same thing, yeah, and now find how many are in that 25 moles, yeah? And the 25 moles is not going to be as much as in the 250, yeah? So you need to divide it by 10, yeah? So in the 25, it's going to be this thing, yeah, 0.1, sorry, 0.00121, yeah, divided by 10, yeah? Because we had, that was for 250, 1 5 for 25, so divide by 10, yeah? And you get 1.21 times 10 to the power minus 4, yeah? Alright, safe. Now what you want to find, yeah? Is how much manganate, yeah, is present in the solution. This C2O4 situation, yeah, this C2O4 here, yeah, you need to find how much manganate, yeah. So C2O4, we know how many moles it is now, yeah? That's the 1.21 times 10 to the power minus 4 moles, yeah? Let me check something. Is that minus 4 or minus 5? 002, 121, yeah? Divided by 10. So minus 4, yeah, what is that? Alright, save. Alright, cool. I'm correct, I'm correct. Alright, cool. Yes, we've got that many moles of this situation, yeah. And we want to find how many moles of the manganate, yeah. So to find how many moles of the manganate, yeah, you're gonna need to divide it by 5 to find how many is in one molecule, and then times it by 2 to get how many is in that. Or you can just times it by 2 over 5. That's the same kind of situation. So you can divide it by 5, then times it by 2 to find out how many in manganate, or you can just times it by 2 over 5. So I'm gonna write that as times 2 over 5, yeah. So N of manganate, yeah. So over 4 minus is gonna be that times 2 over 5, yeah, so 1.21 times 10 to the power minus 5 times 2 over 5, that's going to get you 4.84 times 10 to the power minus 5, yeah, mole. Alright, safe. So now we've got how many moles of manganate, bro, so now it's easy. Concentration is equal to the moles, 4.84 times 10 to the power minus 5. If you're asking why we're finding moles of manganate, it's because that's the answer. It says find the concentration of manganate. So therefore, we got that, bro, divided by it was 23.85 volume, that's in centimeter cube, so divided by 1,000 to get decimeter, and that's going to get you 2.029 times 10 to the power minus 3 mole per dm cube. And I'll obviously write that as 2.03 times 10 to the power of minus 3, 3 significant mole per dm cube. Alright, safe. Alright, safe. Let's look at this situation now, yeah? So, shows the 25, whatever. Alright, cool. E, yeah. Nah, my bad. D. It says, draw the meniscus here. So the meniscus, bro, has to sit. It's got to be a curve. It's got to sit at the baseline. So just draw the base like that and then draw up from it. So it's like a U shape, and the bottom of the meniscus has to touch that graduation mark. You get it? Alright, calm. Alright, E. Potassium manganate is oxidized and harmful, whatever. When filling the burette, yeah, you need to obviously fill out eye level, yeah. This is a common situation because if you don't fill out eye level or below eye level, it's gonna spill into your eye and you're gonna get permanently blind and look like Stevie Wonder. You get me? So dissolving the solid, yeah. Obviously, what we need to do here is we need to do wear glasses, yeah. Obviously, you're dissolving the solid and some shit. Shit could be moving around. Shit could be doing I don't know what. You know what I'm saying? It's doing tricks. Yeah. So what you need to do is you need to wear glasses in it. That's the not glasses, I'm trying shit. Wear gloves, yeah? That's what you need to do here, yeah? Wear gloves, yeah? Alright, calm, obviously. Stating the color change you see in the endpoint of each titration, bro. You're using you're getting the manganate at the end. That's what you're left with here, whatever. Uh and that kind of shit. So obviously it's gonna be what, bro, exactly. Color change is gonna be what? It'll be colorless initially. It's gonna be like a light purple, yeah? So you can say that it's a pink, yeah? That's what they're looking for here. You can say light purple, you can say pink. Obviously it's colors to pink. You already know what's being used there. You get calm. Give two practical steps here needed before recording the initial burette reading. Yeah, so uh listen, fam, you need to remove the funnel. Yeah, since because that could have like excess bullshit inside that can drip into that, and that might like affect the situation. So obviously you need to remove the funnel, and then also you need to ensure there's no air gaps below the tap. So below this tap situation, you've got to ensure there's no air gaps, so it's just solid like that. These are two. If you've never seen them before, you might start tweaking a bit. But trust me, yeah, if you memorize these two, it's always the same. This is what they're looking for, especially this air bubble shit. Right? That, yeah, that's what they're looking for, bro. In this kind of situations, when you're talking about something like this, that's what they need. You'll see it's a common trend in the mark schemes. Alright, so if when Na2C2O4 is added to a solution, alright, calm, whatever, bro. Say nothing, man. Yeah, say nothing, bro. So obviously, yeah, the delta H, yeah. So what I can write here is that delta H, yeah. So changing enthalpy, yeah. So it's gonna be is similar as the same number of bonds, same number and types, yeah, of bonds are broken and made, yeah, because all you're doing here is like a ligand substitution, yeah, so you're just gonna take the whatever and substitute with the other water ligands, yeah, so it's the same kind of bonds as well with the H and O and that sort of shit, yeah, so no problem, yeah, so they're broken and made, yeah, uh, okay, safe. So you talked about delta H, yeah, now I was talking about entropy, yeah, so delta S, yeah, is positive because there's going to be an increase of entropy, yeah, you're adding, like, you're adding this shit, so it's more atoms, you get that, you see how many atoms there are, yeah, you're adding that to the thing, yeah, and replacing it with that. So that's going to be more atoms, yeah, so therefore more disorder, which means more entropy, yeah, so it's positive, yeah, and entropy increases as more molecules are in solution, yeah. Alright, safe. Now what I can say furthermore here is that for the to wrap this up here, get the final marks you need, you obviously need to state the Gibbs free energy equations, which delta G is equal to delta H minus T delta S. And what you need to say here is that since the enthalpy is staying the same, and since S has increased, it's going to be more negative for delta G. So you need to basically just say it's going to be negative, yeah? So to say that the reaction is feasible, yeah? So I can say that delta G is always negative, or is negative as minus T delta S. Don't write T delta S, negative T delta S, yeah? Because if you write T delta S is always negative, it means that negative of that will be positive. So you need to make sure you write negative T delta S is always negative, yeah? Alright, calm. So therefore, and also you can write and, yeah, delta H is negligible, yeah. So what I'm saying is that delta H is not changing between the two ligands, yeah, between the two two whatever you call it, complex ions, yeah. Calm, and hence the reaction is always feasible as delta G is less than zero, yeah. Cool. That's all the marks there. Which polymer has hydrogen bonding between polymer change? Obviously Kevlar. This just comes down to what they're made of, bro. Uh, Kevlar has amine groups, amide groups here, which are gonna have, you get me, and it's whatever, and CO that's gonna cause that. So it's Kevlar. If you haven't seen it before, get to know it now. It will come up in the future. You know it's Kevlar. Which is the repeating unit of a polyamide? For polyamide, bro, you need an N linkage. You need like an NH linkage, yeah. So the only one here that has an NH linkage, yeah, is D, yeah. That's bait, yeah. So this should be obvious, even if you don't know about anything like that. You should be able to clock that's not A or B. Or C for that matter. You should be able to clock that as D. Alright, calm. Which type of polymer? Because you can see the linkage right there. You can't have a shit like this where it's on the edge or something, bro. Alright, cool. Which type of polymer is not hydrolyzed by heating with concentrated aqueous sodium hydroxide? Yeah. So it's the answer is A, yeah, because A has strong CC bonds, yeah. Whereas all the others they have like, they either have like polar bonds or they have some kind of situation where it can easily be susceptible to like, you know, hydrolysis, right? So for example, the polyamide has got CONH, that's easily susceptible, come on. This shit has COO, that's even worse. And this shit is protein, of course, protein can be hydrolyzed there, so it's just A, yeah. So it's like the opposite of question one, question two, which was like which one has the bond like hydrogen bonding, has like good bonding, polar bonding. This is the opposite, yeah. Alright, safe. Which forms a polymer with my man, yeah. So you've got like a diacid chloride situation. Uh which is gonna form a polymer with it. You need something that's gonna bond to both ends. So you see the Cl here, the Cl here. You need like another di situation. So that can't be my man. Can't be my man. It could be my man down there, but like, let's be real here, bro. Yeah, which one are they going for? Yeah, A, where you got two amine groups like that, NH2, NH2 on each side, yeah, or are they gonna go for D, where you got carboxylic acid bullshit and this? Nah, of course not, bro. A, yeah. Alright, come. There's probably some deeper reasoning behind why D is like on another level, but for A level chemistry, it's just obviously A. Alright, calm. Which polymer has a hydrogen bond in between its changes? Yeah, again, bro. Kevlar, yeah. Standard, bro. Alright, save. Yeah. Alright, save. So here we got an isomer, yeah. You want the number of carbon 13 peaks here. So you need to see the different carbon environments in it. So we got one carbon environment here. So that's the carbon environment is like what the carbon's attached to and the bonds that it's attached to. Yeah. So that's the one carbon environment. That's the second carbon environment. That's a third and that's a fourth one. These two are repeats. These two are the same as the ones above here. So hence, therefore, there's four peaks in it. Splitting pattern, yeah. So a splitting pattern, that's gonna be so N has no hydrogens attached to it. We're looking at this alpha carbon here. The carbon that's next to it has two hydrogens, so it's gonna be a splitting pattern of triplet, yeah. 2+1 rule, yeah. So triplet. Explanation. Explanation is that there's two hydrogens on the adjacent carbon. So draw the structure of the isomer C6H16N2 to make nylon 66, yeah. So listen, yeah, it's gonna be this is in the video last time, yeah. Listen, in the content one, yeah, you need to memorize this. You need to make sure you know this, yeah. If you want to get the A star, yeah. It's made by 1,6-diaminohexane, so you should be able to just draw that straight away, yeah. So the formula for that C26 like that, and then N, and then HH, and then same situation here, NHH, yeah. Listen, fam. You should be able to draw this. You shouldn't have to guess this here. You can guess this, obviously, based on this. You know it's going to be like a hexane kind of situation there. You know you got to have the NH2 groups on either side, yeah? So you can guess it, yeah, but you shouldn't have to, bro. Yeah? You should just know this, yeah? Alright, come on. Draw the structure of the isomer that contains two primary amine groups, yeah? Okay, cool. So again, two peaks here. So let's draw the CC here, yeah? Two primary amines, so the amine primaries are going to be here and here. Draw that as H2N instead of NH2. Safe, and then bro, the rest of them is just gonna be CH3 groups in it. So CH3, CH3, CH3. Yeah, the way I know this, the reason I know this is because now we just got two carbon environments. This and this have the same carbon environments. All four of these have the same carbon environments. That's two different carbon environments. So you're gonna have two peaks. Yeah, and that's the only format that you can really have with that. Yeah. Alright, calm. Here we've got two tertiary amine groups here. So draw the tertiary amine groups. It's gonna be N attached to just draw the central carbons, yeah, always draw central carbon first, yeah. Central carbon, yeah. Alright, safe. Now two amines, yeah. So two tertiary amines. So tertiary amine needs to have three R groups, yeah. So that's one R group, two R group, the third R group is gonna come here. So we're using up pairs there. And then N is also gonna have the R groups here, so that's gonna be CH3. I'm alright, and H3C is what it is. CH3 here. Calm. And then yeah, all we can use now is just hydrogen. That's the only thing we're allowed to use because we used up all the carbons here. So just hydrogen, but that should suffice. That's fine. It's got two tertiary groups. It only has two keeps. You only peaks. You only got two different unique carbon environments. One carbon environment. This is the same carbon environment. This is the different ones, and they're all the same. All four of these. You got two different ones there, and these are tertiary amines anyway. So there you go. Yeah, that's the answer for that. Uh, Question 8, yeah. Cool. A repeating unit of a polymer is shown here. Which monomer or pair of monomers can be used to make this polymer here? So obviously, yeah, you go on an amide situation, yeah. So like a diamine, yeah, that's made there, and you got a carboxylic acid situation there. Obviously, a dicarboxylic acid because you got CO there, you got CO there, and a diamine because you got NH, you got NH here. Cool. Obviously, one H has fucked off, one H has fucked off, yeah, as normal, bro, as standard, yeah. So, what's going to be the answer here? Obviously, you're going to need, yeah, so one dicarboxylic acid, or you could also have a diacyl chloride that's also allowed. That could be Cl there, and H, that could be HCl being formed there. So, essentially, yeah, can't be A, can't be B, could be C or D. However, as you see, this has CH2 6, whereas this has CH2 4, impossible to be formed there, so therefore it's going to be C, yeah. Alright, calm. Question 9. The structure or part of polyester chain is shown. Which statement, whatever. Hydrogen bonds, bro. There's no hydrogen bonds in this situation. There is dipole forces like that, but there's no hydrogen bonds. Permanent dipole forces, yeah, that's correct. Then B obviously is going to be weak van der Waal. Obviously, is going to be permanent dipole, yeah, as I've established there. C, the carbon-carbon bonds, obviously that's irrelevant, bro. You can't destroy a covalent bond from melting shit, so therefore it's irrelevant. And same with D, you can't destroy shit by melting it, so they're completely unaffected, yes, so it's irrelevant. So just part B, yeah. Alright, calm. Alright, so if, question 10A, yeah. Give the full IUPAC name of isomer P. Okay, so if let's look at what isomer P is, yeah. So isomer P is this situation here. Uh, this is gonna be pentanoic acid here. That's bait, bro. We've got COOH on the end there. That's gonna be acid. It's gonna be pentanoic with the double bond in the middle, and obviously we've got a methyl group here as well. So this is the highest priority functional group. So let's just call that a one, yeah. Alright, no problem. Now that we established that as a one, then basically everything from that is gonna be. This is gonna also be. This is gonna be one, two. So that's gonna be two methyl, yeah. Uh, the two is also gonna have pentene, yeah, and then just oic acid, yeah. So it's also gonna be a EZ isomer. Is it E or Z? The two higher priority groups are on the same side, obviously that and that. So therefore it's gonna be Z, yeah. Alright, safe. So there we go. We got Z 2 methyl pent 2 in 1 oic acid, yeah. Alright, safe. Calm. Sample P was mixed with excess oxygen and mixture it was ignited, so we're going to have a combustion situation here, yeah? We already know what sample P was here, it gave us the formula above for that. I'm going to go below because more space. So it's going to be C6 here, H12, H10 actually, yeah, O2, plus obviously oxygen, yeah, that's O2. It's going to go to CO2, yeah, carbon dioxide, and H2O. That's just a standard combustion reaction here, yeah? Alright, safe. We need H10, so therefore we're going to need 5 H2Os. If we've got 5 H2Os, 5 times 0 is going to be 5. 5 plus 2 is going to be 7. And on the right hand side, we've got 2 here, 2 there, 4. So we're going to have to balance this out. You need 6 carbons there, bro. So add 6 there and then balance that. It's going to be 7.5. Or I can make that 14, but forget that. We're going to stick with 7.5 here to make 14 on the left hand side for O2, yeah. Plus another 2 there. Alright, so that's balanced now. So now what I need to do is obviously read the question, yeah. When you read the question, it says that the gas remaining was 335, yeah. However, after he reacted, yeah, the volume of gas decreased to 155. So therefore, the amount of CO2 that was used here is 335 minus 155, yeah. So amount of CO2 used there. So CO2 used there is gonna be 335 minus 155, yeah. That's gonna be 180 centimeter cubed, yeah, of CO2 used. Alright, safe. So that's the amount of CO2 used, yeah. Both gases were measured at whatever, alright, no one gives a fuck, bro. No one cares. Alright, cool. So obviously here we don't know the amount of CO2 in moles, yeah. So therefore we're gonna have to obviously use the formula. The formula that we're gonna use is obviously PV equals nRT. PV is equal to nRT, safe. And now obviously that means that N is equal to PV over RT. Safe. P is obviously Pascal, is 105 kilopascal, which means that's going to be 105,000 Pascal, yeah? No problem, no problemo, fam, as the Spanish say, yeah? And obviously now what you want to do is this bracket here is obviously going to have, use logic here, 180 centimeter cubed. So what you want to do there is you want to cube root that to turn it into cm, then you want to change it into m from cm, yeah? And then obviously cube that again. And when you do that, you're going to be left with 180. So just to follow that, yeah, cm cubed. You want to go to cm, then change that to meter, and then cube it again to get meter cubed. And you'll get 180 times 10 to the power minus 6, or 18 point whatever, or 1.8 times 10 to the power 7 minus 8, or whatever, minus 7. Alright, safe. So what you want now is obviously R is just standard, bro, that's 8.31. And then KT is Kelvin, 298 Kelvin, yeah? Alright, safe. Put that in the calculator, we're going to get 7.632 times 10 to the power minus 3 MOL. That's moles, yeah? Moles of CO2 produced. That's the amount of moles of CO2. Now we want to find the moles of the actual shit that we want, which is that N of C6 bullshit, yeah? So N of C6 H10 O2, yeah? So how many moles of that are we forming? Well, let's look at the equation above. For every 1 mole of man, we've got 6 moles of man. So you need to times that by 1 over 6, or otherwise divide it by 6 to get the moles of this. So the moles of this is going to be 1 over 6 times 7.632 times 10 to the power minus 3. That's obviously because this is the moles of CO2. So therefore, if you want the moles of the other one, it's a 1 to 6 ratio. You divide by 6. You get me? Yeah. So after you do that, after you input that into the calculator or into your brain, yeah, and you'll find that it's 1.272 times 10 to the power minus 3. Now, after this here, you want to find the MR of this here. I'm not going to do it, but 12 plus 10 plus 2 times 16 times the however many 12 for 6 is going to get you 144 apparently. 114. So now you need to do mass is equal to N times MR, which is going to be 144 times by 1.272 times 10 to the power minus 3. That's going to be equal to 0.145 Gs here, which is going to be, they want it in milligrams here, so it's going to be 145 mg, and that's the final answer to that situation there. How many marks is that? Yeah, 5 marks, easy. Yeah, straight swept up like that. Yeah, calm. Let's move on now. We're looking at question C. Yeah, so C is talking about some compound. It's telling us, oh, okay, use a spectral in your statement state or whatever, bro. Alright, safe. Yeah, so what we're looking at here is a cyclic compound of C6H10O2. Alright, safe. So let's look at the peaks. Let's look at figure 1. Yeah, figure 1 has a mad peak over here. What's that peak saying? It's in the 2,500 to 3,000 range. Yeah, if you look at the infrared environments here, we can see that that's going to be acid in it. So therefore, you want to write that over here. So write, okay, nice. So that's going to be OH acid, yeah? Alright, safe. Now we look at the second situation. Obviously, we've got 4 carbon peaks here. 1, 2, 3, 4. So that tells us that there's 4 different carbon environments here. So you can say, alright, cool. 4 different carbon environments here. Now let's look at what those carbon environments actually are, yeah? If we do that, we can see that this situation here is in the 180 to 200 kind of range, yeah? According to my calculations here, that's about a CO in it. That's going to be ester or acid, yeah, at 160 to 185 here. So therefore, I can say that it also has a COO peak, and it also has a another peak over here. Let's see what the other peak is saying. In that 40 to 60 range, we got a little bit of a peak there. What's that peak saying? It's saying COOH CH3. So this peak here, that 20 to 50 range, that's that peak there in that 20 to 50 range, as you see, yeah. So therefore, it's also going to have a RCOCH bullshit kind of thing, yeah. CH3 or whatever, it doesn't really matter. Alright, cool. Or C, could be C, anything, yeah. Just write as CH. Alright, safe. So because we've determined those two things here, that means that it's gonna have that a CO kind of situation, and it's gonna have the COOH. So now we know that it's cyclic here, and we know how many carbons are in this situation. We know that it's gonna be C6H10O2. So hence what I can draw here is I can just draw a standard situation, a hexagonal kind of figure, pentagonal actually, yeah, because one of the carbons is getting used for the other situation. So therefore, I'm gonna draw it like that. 1, 2, 3, 4, 5. And then obviously you need that carboxylic acid end there because it's acid OH acid. So you get that. This adds up to the same amount of carbons. This is actually what they're searching for here. This is all you need. Now you just want to confirm that there's 4 different carbon environments. That's calm. This is the first carbon environment. This is the second carbon environment. This is the third. This is also the third. They're the same carbon environments. And these two are the same shit as well. So as a result, we've got 4 carbon environments here. Remember, carbon environment means what it's around, if it's around the same kind of shit. If it's around the exact same thing, then it's the same carbon environment. Alright, cool. No problem. D, yeah? Isomers R and S are shown. Although the C13 spectra of R and S both show the same number of peaks, the spectra can be used to distinguish between the isomers, yeah? Give the number of peaks for each isomer, yeah? So, okay. Okay. Let's use logic, bro. Let's use logic. Let's use logic, okay? Okay. How many peaks? How many peaks? Number of peaks here. So how many peaks? So how many different environments are there, okay? This is one environment, okay? Can we all agree on that, yeah? This is a second environment, okay? This is a third environment. This shit is the same as the shit before it. So this is also environment number 3. That image looks crazy. I could get demonetized for that. That's an arrow, yeah? Okay. See? Is obviously the second carbon environment that's there. That's the same shit. The first one, again, number 1 is here. So we've got 3 different peaks. Now I could do the same shit here. 1, 2, 3, that's 3, that's 2, that's 1, yeah? No problem. Symmetry, yeah? Like what you learned in year 3. So now obviously that's going to be 3 peaks here for both of them. So both have 3 peaks, yeah? Alright, safe. What the fuck am I writing, bro? Peaks, yeah? Alright, cool. So that's going to be 3 peaks here. Now you need to look at the justification. I like it when they use them words, yeah? Justification, yeah? Alright, cool. So give the number of peaks of each as shuts, bro. Alright. Alright, cool. Alright, we need to chill out. We need to chill out, okay? Let's look at our little thing here. In the 20 to 50 range, we have that RCOCH kind of group, yeah? Now, if you think about this, yeah? How many of my man do we have over here? Here we've got 2. We've got this shit here, and we've got this shit here. And that's going to be mirrored. We've got that shit there, and that shit there. 1, 2, and 1, 2 are exactly the same. So we've got 2 different kind of leading groups there, 2 different peaks here. Do you get that? So R has 2 peaks. It has the peak there, and the peak there, and this shit is repeated. My man only has 1 peak. Yeah? The reason he only has 1 peak is because attached to this C is only 1 piece, and attached to this C is only 1 piece, not 2 pieces on each end, yeah? So therefore, in this range, so in terms of this thing, they only have what the R has 2 of these situations, and S has 1 of these situations. You get it? So therefore, R is going to be so in 20 to 50 range, yeah, R has 2 peaks. Okay, cool. Now, how many carbons here does R have next to the CO bond? Next to the CO bond, we got 1, 2, and 3, 4 next to that one. So hence we got 4 carbons next to the bond. However, S only has 2 carbons that are next to that bond. So we can also write that. So hence I can write that. I like how this sheet yeah is meant to be about polymers, yeah, but it just ends up being about NMR and shit. That's just how it is, isn't it, man? Alright, cool. E. Yeah, that's it. I'm pretty sure that's it for that question. Yeah, that's it. Alright, cool. E. Although the 1H spectra of R and S show the same number of peaks, the spectra can be used. Okay, cool, bro. Calm. Let me draw the shout again, man. Okay? C, CH2, CH2, C double bond O, and CH3. That's the situation we had on the left here. Okay, safe. Safe. Let's look at how many hydrogen environments now, yeah? Okay, okay, okay. How many peaks is it gonna be? 1. This is the same shit. 2 and 2. We got 3 different hydrogen environments, yeah? So hence we got 2 for R. And guess what? They're asking for number of peaks. I'm assuming they're both the same, yeah? I don't even need to draw it. I don't know why I drew it out, yeah? We can just use this. So now let's look at S here. Same shit. 1, 1, and this is the second one. That's the second one. They're identical. Hence we got 2 pieces for both of them, yeah? We got 2 peaks for both, yeah? So number of peaks here, 2. Alright, come. 2, yeah? Save. So we've got 2 peaks in both here. Now, it's going to be talking about the splitting patterns and shit, yeah? So you need to talk about the singlets, triplets, the 2 plus 1 rule, all of that shit. So what you need to say, yeah, is that what I need to say here, basically, is I need to look at this situation, yeah? So let's look at R, yeah? So R, I don't know why I drew that out. I thought I was the guy drawing that out, innit, bro? I can just look back here, yeah? So obviously R has what, bro? R has, um, R has a situation. So in terms of singlets and triplets and shit like that, yeah, you need to look at the C that you're looking at, the H thing. Is there a change in hydrogen environments? If there isn't, then there's no change. You get me? So let's look at my man. We've got H3C. Yeah, is it the adjacent carbon that's attached to has no hydrogens, so there's nothing there. It's just single. You get it? Now let's look at C. CH2, yeah? Calm. So H, the ones that are H's are attached to, yeah? We got my man with nothing, and we got my man with the same environment. If it's the same environment, it counts as nothing. So therefore, that's also nothing. This guy also has nothing, and this guy has the same environment, so it's also nothing. My man is attached to carbon with nothing. So we just get singlets there. You get it? So therefore, R has a singlet. Has two singlets, by the way, if you look at that properly, yeah? Two singlets here. Has singlet there and singlet there, because it's literally a mirror, bro. Alright, calm. And then S here, S is a little bit more interesting, yeah? It's a little bit more interesting. CH2, my man has three on him, yeah? Because he's got three on him, it's therefore gonna be a what? It's gonna be a, first of all, let's talk about my man H3C, yeah? My man's got a CH2. This guy's got a CH2. That's a different environment to my man. How is it different? He's got two hydrogens. Two hydrogens, 2 plus 1 is 3. So that's going to be a triplet because if you had none, that would technically be a singlet. So it's like 2 plus 1. You get me? So you have to add another 1. So that's going to be triplet, yeah? So S has a triplet, yeah? And A. So now this one has three attached to it, yeah? Again, this is a mirror, yeah? So it doesn't matter what's going on the right hand side, it's the same shit. Okay, cool. So H3C has three. 3 plus 1 is 4. So it's gonna be whatever the thing for 4 is called. I really can't remember right now. I think it's called a quintet or something. Quartet. So it has a triplet and a quartet. That's a splitting pattern, bro. You get it? So S has a triplet and a quartet. So that's what they want to see. That's the answer to this, yeah? Alright, come on. Alright, save. Yeah, calm. So action of 5-hydroxyhexanoic acid here can lead to two different products here. On general heating can cause a cyclic compound here. Under different conditions, it can form polyester here. So just draw the situation that you got here. So the 5-hydroxyhexanoic acid here, again, bro, like if you want to get that A star here, you gotta be willing to get like dirty with it. You get me? Gotta be willing to get like gritty, fam. Yeah, start drawing shit out. Like I know it seems like fugazi at first, but trust me. Alright, that's one, two, three, yeah. One, two, three, four, five, six, yeah. Alright, calm. Alright, safe. And then obviously this is a 5-hydroxy, yeah. So this is technically one because highest priority group. So this is number 5 over here, yeah. So this is gonna be OH. The rest is all gonna be H, yeah. So just draw that in. H, 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 H. Alright, safe. Cool, yeah. Safe. So what's gonna happen, yeah? Cyclic compound, obviously that is gonna rejoin with the other side, yeah. It said it's done this by losing water, yeah. So therefore, if it's done this by losing water, the OH is obviously gonna get deleted, yeah, and obviously the H from here is gonna get deleted. So therefore, you're gonna get left with if you think about it, the CO is gonna be formed, yeah. So you're gonna get like this kind of situation. You're gonna get a cyclic thing like that, yeah. The CH3 here is gonna come as like a side link. You see that CO? Because the H is gonna go, that CO, that O bond is gonna link back to the C. So it's gonna create like a CO kind of situation here. You get it? And then this C, this HCH3 here is gonna be like a side link there. It's gonna be H3C. And then over here, just reform that there. One, two, three, four, five, six. And then here is going to be a double bond O from my man over here that I've also got formed. And that's going to wrap around on the C that way as well. Yeah, back to the CO there. You get the situation. So that's going to be an O there. So that's the situation they're looking for here. Alright, safe. And now with the whatever, the polyester, yeah, that's obviously going to be a CO kind of linkage, yeah. So it's going to be same thing, CO on the left here. So again, this CH3 is going to be like an additional part to C. And H is also going to be removed from there if you see that. So the OH is going to react with the OH here. H is going to get removed. OH is going to get removed fully. And we're going to be left with O there, double bond here. And it's going to wrap around. So it's going to look like this basically. This is the polyester that they're looking for, the repeating unit. O, C, just the rest of the C's. 1, 2, 3, 4, 5. O still has that. H everywhere, bro. And this is going to be CH3, H. Yeah. So if you don't understand that, what I'm talking about is that because that's going to react with that, yeah, this is going to delete, yeah. this is gonna, one of those is gonna be the condensation reaction, yeah? So it's gonna be CO, and it's gonna wrap around to my man, and then to my man here, and then this CO is gonna be left off, it's still gonna be there. And this CH3, I can write that as like a bond on here and just shorten it, you get me? So that's why I did it like that. So CO and then CH3 is shortened like that. Alright, calm. So repeating unit point, the type of polymerization, obviously that's going to be condensation, yeah? So condensation polymer. Let's save. Alright, G, yeah? So listen, yeah, if you got some bullshit like that, yeah, just write it in like a nice form. So write it as C with two H's, double C like that, yeah? So like this. So CC, and then this is bonded to two H's, yeah, that's the H2 there. And then here, that's the COOCH2 bullshit. CH3, yeah, that's CH3 there. Alright, safe. So now just draw the repeating unit is very easy, yeah. All you need to do, yeah, is just delete one bond there, so it's just CC, calm. My man is gonna go up now. So that's COO, CH2, CH3. My man's gonna go there, CH3, and then these are HH here. And now just extend it. That's it. That's literally it. That's the answer, bro. Yeah, easy, yeah. Alright, calm. Then it says justification for why it's not biodegradable. Obviously, it's because it has non-polar CC bonds. I'll make it bigger in a minute. Therefore, cannot be hydrolyzed here, or cannot be susceptible to nucleophilic attack, or whatever you want to write here. Because you got those CC bonds, strict full line CC bonds, bro. That ain't, you know what I'm saying? That ain't degrading, bro. Alright, cool. Next one, question 11, yeah. Which compound can be a form of polymer without needing another one, yeah? So that's obviously going to be C. The reason why it's C is because I got an acyl chloride situation here, which is obviously highly reactive, yeah? And so that can self-condense with this hydroxy group there, yeah? Using nucleophilic substitution to obviously make an ester COO, yeah? And then also HCl as a byproduct with that. So you see that COO link there with that O, that's going to be CO, and then the H and the Cl is going to be HCl leaded off, yeah? You can't do with D because you've got carboxylic acid and you just got Cl. Cl is not as reactive on its own as acyl chloride, which is COCl, yeah? You also just know that from the mechanisms and shit. You could also say B as well, because that's going to form like a anhydride kind of situation or like a cyclic anhydride or polymer anhydride, but I don't think they expect you to know that in A level in it. I think that's beyond that or some shit. So yeah, I think what they're looking for here is obviously C, yeah, because that's based on what you know, yeah. Alright, calm. Also for B, you might need some other shit as well. Fuck knows. Alright, cool. Which polymer is likely to be, that's obviously going to be C, polyethane. Yeah, you've got non-polar bonds, it's just C, C all the way. Obviously, the other one's got different types of bonds and shit like that, and dipoles and whatever. C is obviously going to be the one, yeah. Alright, calm. Alright, calm. Final question, yeah. Alright, draw the structure of the monomer used to form polymer P, yeah. Alright, so this is easy. You got CC, it's obviously going to be a double bond, yeah. That's formed by an ethene, yeah. It's going to be a double bond, yeah. And yeah, that's literally it. Just draw a double one, bro. So C double bond C, Cl, CH3, H, and then CH3, yeah. Alright, save. Name the type of polymerization, yeah, that's going to be addition polymer. There's no water being formed, it's not condensation. You've got the same polymer adding to itself, yeah. So it's going to be addition polymer, yeah. Alright, save. Pretty sure addition's got two T's, but who gives a fuck? Alright, cool. Question B, yeah. Draw the structures of two compounds that form together to make compound Q, yeah. That's easy, bro. Take this linkage away, yeah. That's gonna be OH and OH, yeah. That's base. So that's gonna be CCOH, HH, and then the rest just stays the same, and then OH, and then the rest stays the same here, such as CH3, CH3, yeah. Alright, calm. That's that there, yeah. And now the right hand side, same kind of thing. So imagine the O was there. That's also going to be OH situation. That's also going to be an OH situation, yeah. And then an OH here as well. So that's easy, bro. That's literally that's pattern, bro. And the rest just stays the same. So again, that could be an OH situation. So it's just like HO C double bond O. Just copy the whole thing out. So That's CH3, I believe. It was CH3, right? Yeah, so CH3, and then CHH. Cool. And then C double bond O, and then just OH. Again, you can see how that's going to form that polymer there using condensation reaction. It's going to form that. Safe. Oh yeah. You know what, yeah? When you write, oh yeah, if you give the examiner, yeah, two options, yeah, you give him both answers that could be there. That's gonna cause him to shit bricks. You get me? That's gonna cause him to start getting scared. He's gonna start shaking, bro. Yeah, because he realizes, yeah, that you're so ahead of the game that you know both answers. I could also just write that as an acyl chloride as well. Think about it. I could write that as acyl chloride here with Cl at the end. It's gonna react with hydrogen here to make HCl and gonna form another ester link there, like the COO or whatever. Yeah. So what I can just say is draw the same shit, but instead of OH, it's just Cl. It's an acyl chloride. Yeah. So therefore, I can put ClCO uh CH3, same thing, yeah, CH3, C double CHH, and then C double one O, yeah, and then CO. You get me? Acyl chloride reacting to that, yeah. I just spoke about last question how that's gonna be reacting, yeah. Obviously nucleophilic, whatever. So there you go, bro. You get me? Same shit. Alright, cool. C. It's just an environmental advantage of polymer Q, yeah. So if you look at polymer Q, it's got like bare COO bonds. Obviously, those are polar, fam. It's going to be delta positive, delta negative, yeah, which means that they're going to be susceptible to nucleophilic attack or whatever. So therefore, yeah, and P obviously doesn't have any of that, it's just straight chain. You get me? So just say that biodegradable. And then here, yeah, CO is polar in Q, but there's no polar bonds in P, hence can be attacked by a nucleophile, yeah. Calm. And that's the end of that, yeah. Safe.